So far we've talked about, general rates of reaction, and that was this, kind of general delta, of a concentration or a pressure of a molecule over a change in time. And we just talked about rate expressions, which give us a sense of, rate and order. But if you think about it, like with general rates, we're just talking about, how concentration changes over time. Right? With rate expressions, this is more of now looking at how rate changes with molecule concentration or pressure. And so that brings us to the third piece, which is really a combination of those two, which is integrated rate laws. And this is actually now combining kind of the two and looking at how concentration changes with time. And it's not a delta in terms of change. It is actual concentrations or pressure. And so it's really a combination of the rate expressions that we have there from Roman numeral 1 and Roman numeral 2. So we think about A going to products as like a very general reaction. So far we know kind of two things. From, one thing that we know is that the rate would be equal to our change in concentration or pressure of A over change in time, and we would have that negative sign, right? That's Roman numeral 1. That's our general rate, or average rate. And then from Roman numeral 2, we would say that, okay, let's say that this is a zero order process. So that means that our rate would be equal to little k times the concentration of A to the 0 power. So we have our general reaction, we have a zero order process, and we have these two ideas, and notice that our rates, are both there, right? Meaning that we're talking about the same reaction. We should be able to set them equal to one another. Meaning the change in concentration of A over the change in time should be equal to our rate expression, little k times A to the 0 power. If we rearrange that a little bit, if I take over my negative sign and my denominator, right, I would have negative k times the concentration of A naught, or to the 0 power, times then our delta t, or our change in time. Remember, anything raised to the 0 power is 1, So this simplifies to give me this type of expression where I have a change in concentration is equal to negative K times my change in time. And so here's where we now can integrate our values. We can look at our range of concentrations from A initial to A at some concentration of time is equal to negative our integration of our time component, which would be K dt. So here is where we have our integrated form. Don't worry, I'm not worried about calculus or integration here. I'm just showing you how this equation is going to come to play. And so once we solve for that, using this integration motif, we get something that looks like this. Where we have concentration of A at some time point is equal to negative KT plus the concentration of A initially. So we have our concentration or pressure at time point T. We have our rate constant. Remember, that's in 1 over time. We then have our time point. And then we have the initial concentration or pressure for the beginning of the reaction. And so here is one form of the integrated rate law for a zero order process. There is also half-life. Half-life is the time it takes for the concentration or pressure of a molecule to drop by 50%. So we also see this term half-life, and to be honest, that's the most important type of term to really kind of point us to using these integrated rate laws, is that you'll always see mention of half-life within a particular question. So if we take our expression at the very top, and I'm just going to write that again so we can now kind of look at half-life. So at halfway, right, we could say that means the concentration of A at some time point would really be 1/2 the initial concentration. So if we plug that into our expression, you get something that looks like this. And now if we kind of just try to start to isolate time, we would get 1/2 A naught minus A naught is equal to negative KT. So just kind of collecting like terms here. That would give me a negative 1/2 of A naught is equal to negative KT. And then if I divide over my K, I get my time is equal to A naught over 2K. And that is known as our half-life expression. And so we tend to put this T 1/2 to designate that fact. So for a zero order reaction, we have two rate expressions. We have the linear fit so there's our one equation that we have, and we can plot that, right? In terms of our y would be our concentration of A, our x is our time, and we would end up with something that looks like this, where we have a slope equal to negative K. And we have here our y-intercept, which would be the concentration initial of the molecule A. So that's the linear fit. We see the y is equal to mx plus b, expression here. And so that's how we can simply do a simple plot of concentration versus time, and from that we can actually figure out our rate constant. So we have a linear fit, and then we also have a half-life. And so for our half-life, that expression is, our concentration of A initial over 2K. And so what we find with these integrated rate expressions is just this, that we always tend to have two equations. One is the linear fit, and then one is the half-life expression. If we go back to our general reaction, and now let's look at a first order process. We can do very much the same type of mathematics that we had done, in our zero order derivation. I'm not going to go through all that again, but we could say, kind of the similar, at least the beginning, to kind of get that idea, right? That we're still going to have this negative concentration change of A over a change in time, and now the difference really is in the order that we see being now a first order process. And so we can do very much the same type of work to get at our integrated rate expression. And so what we find is that with some calculus, right, or integration, we end up with this type of linear fit. So here is the linear fit that we have for a first order process in terms of our integrated rate laws. And so we still have our y is equal to mx plus b motif. We're just plotting things a little bit differently in terms of, well, we're still plotting time in the x-axis, but now we're looking at the natural log of the concentration. And so we still get this negative slope as we go forward. And there would be our y-intercept. So that's the natural log of our initial concentration. And our slope here is negative k. We also have a half-life expression as well. And that's T1/2 is equal to 0.693 over k. So those are the two expressions for first order processes. And we can plot it and we get a straight line, then we know that we're following a first order plot. The last one is second order. So we can, kind of look at the same type of general reaction, but now looking at second order. And so we can do all the kind of the same things. So now we're in that exponential relationship. And then that leads us to our linear fit, right? We got to do some of our calculus to, an integration. And so here we find there's an inverse relationship that now we have 1 over concentration at time point is equal to kT plus 1 over the initial concentration of A. So there is our linear fit. Again, we still have the y is equal to mx plus b motif. And we can still plot that in terms of time versus now 1 over concentration. And in this case, we get a straight line with now a positive slope. If I can draw a straight line. There we go. So we have here, again, still our y-intercept. So that's our 1 over our initial concentration. And here our slope is equal to little k. And our half-life expression for this is then 1 over little k times the initial concentration of A. So that is our half-life. So a lot of equations there might be getting jumbled up, so let's just kind of summarize. So we have, first zero order. And we have our linear fit. And we have our half-life. So there are the two expressions that we see for zero order reaction. We then have a first order reaction, which is the natural log version of the linear fit. And the half-life that we see for a first order is 0.693 over K. Sometimes we see an alternate form, which is the natural log of A naught over A sub t is equal to negative kt. I just manipulated that first order process as far as the linear fit is concerned. Just now we take the natural log of that ratio, and this is often used when percents are present. Like what percentage of this molecule is left over, or something of that nature. So we do have an alternate form of our first order process. And then lastly, we have our second order. And so that's 1 over the concentration of A at time point t times kt plus 1 over the initial concentration of A. And the half-life for it is equal to 1 over K times the initial concentration of A. So those are our three expressions that we see in terms of both half-life and linear fit. Now, why is this useful? Right, this is useful because now I do not need to run a lot of experiments to figure out reaction order. Like we did earlier. With these, I simply plot my A versus time. And depending on what provides a linear fit, whatever provides a linear fit is then the order of the process. So, for example, let's just keep going with our general reaction. And we don't know what the reaction order is. So I do an experiment. And I measure the concentration of A at many time points. I then plot concentration of A versus time. If I get a straight line, or another way to say that is linear fit, then I know reaction is zero order. If not, then I go to the next plot. So then I plot the natural log of concentration versus time. Again, if I get a straight line or my linear fit, then I know reaction is first order. If not, go on to next. Right, so it's these plots that we're doing in terms of the linear fit, concentration of A versus time, or natural log of A versus time, right? And if we just get the straight line, then we can immediately say, oh, it has to be zero, or oh, it has to be first order. And so then you plot 1 over concentration versus time, and this would be then a second order process. And again, if not, I go to the next. So there's many of these integrated rate expressions. We're only going to deal with, much like we started, with zero order, first order, and second order. So that's why these integrated rate laws are utilized quite a bit. It helps to simplify the process of figuring out the kinetics, figuring out the reaction order with respect to one molecule or another, by just doing simple plots and seeing if we get some linear fits. Let's look at an example of this. The first atomic explosion occurred in New Mexico in July of 1945. What percentage of radioactive strontium-90? Strontium-90 has a half-life of 28.8 years. So how much of that will still remain as of this July 2020? So that's our first question. One thing that we really need to kind of remember here is radioactivity is always first order. So we have this radioactive strontium-90, and so we know that that has to go by a first order plot. We also know we need to use integrated rate laws because of half-life, which we see here. So if we put that together, that means that we have, a first order process, meaning that we would have the natural log of our concentration of A at some time point is equal to negative KT plus the natural log of A initial. And we also know our half-life is equal to 0.693 over K. And, with the integrated rate laws, we tend to always use both the half-life and linear expressions during calculations. So we know what we need to do or use. We know the equations to use, but now we got to figure out, some of the other pieces to the puzzle. One thing that they're asking us for is a percentage. And we also have then the idea of time in terms of July 2020 to or July 1945 to July 2020. So from that angle, in terms of the idea of percent form for my first order, it's going to look more like this. Oops, sorry. Where I have the natural log of A sub t over A sub naught is equal to negative KT, because here is where I find my fraction, which if I multiply by 100 is my percent. So that would be the equation I would like to use, and so I'd be trying to solve for in the orange box. But if you notice, I'm missing two of the elements on the right. I'm missing, not only that box, but I don't have the little k, and I don't have time yet. I do have access to time. Right, my time, or t, would be 2020 minus 1945, or we would have 75 years as far as my time frame goes. But I still need to solve for my little k. So the first step, we're going to use half-life to solve for k. And then second, we're going to use the first order linear fit to solve for the percent strontium-90 remaining. So if we start with step 1, we're just looking at that half-life expression. We do know what the half-life is. It's 28.8 years. So K would be equal to 0.693 over 28.8 years, and we get a value of 2.406 times 10 to the negative second years to the minus 1. So there is our half-life expression. And now we can use our half-life linear fit, but I'm going to use the percentage form so that we can then figure out, the question, the percentage. What is the percentage of that strontium-90 that's left over? So we now can plug everything in that we have. We got our K in step 1. So that's the 2.406 times 10 to the negative second years to the minus 1. We figured out our time was 75 years from the difference of 2020 and 1945. One thing we want to be wary of is consistent units, which we do have here in terms of our year idea, so that those years are canceling out, which we want. And so the natural log then of that ratio of the strontium-90s would be equal to negative 1.8046. We can then get rid of the natural log by taking e to the x of both sides. So that liberates the ratio of the strontium-90. And then we have e to the negative 1.8046. And so our ratio of strontium-90 at 75 years would be equal to 0.1645 or 16.45% of radioactive strontium-90 remains in 2020. It's kind of the problem with radioactivity, is it's always hanging around. That's over 75 years, and we still have an ample amount of this radioactive strontium-90 giving off radiation, potentially doing biological harm. But that's a topic for another day once we get into nuclear chemistry. This is the deal with integrated rate expressions. The big, kind of tip-off is the idea of half-life. You're going to see half-life, or it's going to be asking you for half-life. It's going to be a mention of half-life within the question, and that's what really spurs us on to then using the integrated rate laws. You just then have to know the exact order, and then you just pick the correct equations for that order, and basically plug and chug throughout the setup. So that's integrated rate laws.